as a PDF or a PowerPoint. There's a lot of options here, and you can customize everything that's on here. Now, I just want to show you one more thing that makes your life so much easier in SPSS. You see right here that it's putting down these commands. It's actually saying graph and then histogram normal equals value. And then down here, we've got this little command right here. Most people don't know how to save their work in SPSS, and they kind of just have to do it over again every time. But there's a very simple way to do this. What I'm going to do is I'm going to open up something called a syntax file. I'm going to go to New, Syntax. And this is just a blank window that's a programming window. It's for saving code. And let me go back to my analysis I did a moment ago. I'll go back to Analyze. I can still get at it right here. And Descriptives and Explore. And my information is still there. And what happens here is even though I set it up with drop-down menus and point and click, if I do this thing paste, then what it does is it takes the code that creates that command and it saves it to this syntax window. And this is just a text file. It saves it as .sps, but it's a text file that can be opened in anything. And what's beautiful about this is it's really easy to copy and paste, and you can even take this into like Word and do find and replace on it. And it's really easy to replicate the analyses. And so for me, SPSS is a good program, but until you use syntax, you don't know the true power of it, and it makes your life so much easier as a way of operating it. Anyhow, this is my extremely brief introduction to SPSS. All I want to say is that it's a very common program, kind of looks like a spreadsheet, but it gives you a lot more power and options, and you can use both drop-down menus and text-based syntax commands as well to automate your work and make it easier to replicate it in the future. I want to take a look at one more application for coding and data science that's called JASP. This is a new application, not very familiar to a lot of people and still in beta, but with amazing promise. You can basically think of it as a free version of SPSS. And you know what? We love free. But JASP is not just free, it's also open source, and it's intuitive, and it makes analyses replicable, and it even includes Bayesian approaches. And so take that all together, we're pretty happy and we're jumping for joy. So before we move on, you just may be asking yourself, JASP, what is that? Well, the creators emphatically deny that it stands for just another statistics program, but be that as it may, we'll just go ahead and call it JASP and use it very happily. You can get to it by going to jasp-stats.org, and let's take a look at that right now. JASP is a new program. They say a low-fat alternative to SPSS, but it is a really wonderful, great way of doing statistics. You're going to want to download it, specifying your platform. It even comes in Linux format, which is beautiful. And again, it's beta, so stay posted. Things are updating regularly. And if you're on Mac, you're going to need to use Xquartz, but that's an easy thing to install. It makes a lot of things work better. And it's a wonderful way to do analyses. When you open up JASP, it's going to look like this. It's a pretty blank interface, but it's really easy to get going with it. So for instance, you can come over here to File, and you can even choose some example data sets. So for instance, here's one called Big Five. That's personality factors. And you've got data here that's really easy to work with. Let me scroll this over here for a moment. So there's our 5 variables. And let's do some quick analyses with these. Say, for instance, we want to get descriptives. We can pick a few variables. Now, if you're familiar with SPSS, the layout feels very much the same, and the output looks a lot the same. All I have to do is select what I want, and it immediately pops up over here. And then I can choose additional statistics. I can get quartiles. I can get the median. And you can choose plots. Let's get some plots. All I do is click on it, and they show up. And that's a really beautiful thing. And you can modify these things a little bit. So for instance, I can take the plots, and let's see if I can drag that down. And if I make it small enough, I can see the 5 plots. Well, I went a little too far on that one. Anyhow, you can do a lot of things here, and I can hide this. I can collapse that, and I can go on and do other analyses. Now, what's really neat though, is when you navigate away from it. So I just clicked in the blank area of the results pane. We're back to the data here. But if I click on one of these tables, like this one right here, it immediately brings up the commands that produced it. And I can just modify it some more if I want. Say I want skewness and kurtosis. Boom, they're in there. It's an amazing thing. And then I can come back out here. I can click away from that. And I can come down to the plots, expand those. And if I click on that, it brings up the commands that made them. It's an amazingly easy and intuitive way to do things. Now, there's another really nice thing about JASP, and that is that you can share the information online really well through a program called osf.io. That stands for the Open Science Foundation. That's its web address, osf.io. So let's take a quick look at what that's like. Here's the Open Science Framework website, and it's a wonderful service. It's free, and it's designed to support open, transparent, accessible, accountable, collaborative research. And I really can't say enough nice things about it. What's neat about this is once you sign up for OSF, you can create your own area. And I've got one of my own. I'll go to that right now. So for instance, here's the data lab page in Open Science Framework. And what I've done is I created a version of this JASP analysis, and I've saved it here. In fact, let's open up my JASP analysis in JASP, and then I'll show you what it looks like in OSF. So let's first go back to JASP. And when we're here, we can come over to File and click Computer. And I just saved this file to the desktop. Click on Desktop. And you should have been able to download this with all the other files, DSO324JASP. I'm going to double click on that to open it. And now it's going to open up a new window. And you see I was working with the same data set, but I did a lot more analyses. I've got these graphs. I have correlation scatter plots. Come down here, I did a linear regression. And we just click on that and you can see the commands that produced it as well as the options. Didn't do anything special for that, but I did do some confidence intervals and specified that. And it's really a great way to work with all of this. I'll click back in an empty area and you can see the commands go away. And so I've got my output here in JASP. When I saved it though, I had the option of saving it to OSF. In fact, if you go to this web page, osf.io/3t2jg, you'll actually be able to go to a page where you can see and download the analysis that I conducted. Let's take a look. This is that page. There's the address I just barely gave you. And what you see here is the same analysis that I conducted. It's all right here. So if you're collaborating with people, or if you want to show things to people, this is a wonderful way to do it. Everything's right there. Now this is a static image, but up at the top, people have the option of downloading the original file and working with it on their own. So in case you can't tell, I'm really enthusiastic about JASP and about its potential. Still in beta, still growing rapidly. I see it really as an open source, free and collaborative replacement to SPSS. And I think it's going to make data science work so much easier for so many people. I strongly recommend you give JASP a close look. Let's finish up our discussion of coding and data science, the applications part of it, by just briefly looking at some other software choices. And I'll have to admit, it gets kind of overwhelming because there are just so many choices. Now, this is in addition to the spreadsheets and Tableau and SPSS and JASP that we've already talked about. I mean, there's so much more than that. I'm going to give you a range of things that I'm aware of, and I'm sure I've left out some important ones or things that other people like really well. But these are some common choices and some less common but interesting ones. Number one, in terms of things that I did not mention, is SAS. SAS is an extremely common analytical program, very powerful, used for a lot of things. It's actually the first program that I learned. And on the other hand, it can be kind of hard to use and it can be expensive. But there's a couple of interesting alternatives. SAS also has something called the SAS University Edition. If you're a student, this is free. and it's slightly, reduced in what it does. But the fact that it's free, and also it runs in a virtual machine, which makes it an enormous download, but it's a good way to learn SAS if it's something that you want to do. SAS also makes a program that I really love were it not so extraordinarily expensive, and that is called Jump. And it's a visualization software. Think a little bit of like Tableau, how we saw it. You work with it visually, and this one you can drag things around. It's a really wonderful program. I personally find it prohibitively expensive. Another very common choice among working analysts is Stata, and some people use Minitab. Now, for mathematical people, there's MATLAB, and then of course there's Mathematica itself, but that's really more a language than a program. On the other hand, Wolfram, who makes Mathematica, is also the people who give us Wolfram Alpha. Most people don't think of this as a stats application because you can run it on your iPhone. But Wolfram Alpha is in fact incredibly capable. And especially if you pay for the Pro account, you can do amazing things in this, including analyses, regression models, visualizations. And so it's worth taking a little closer look at that also, because it actually provides a lot of the data that you need. So Wolfram Alpha is an interesting one. Now, several applications that are more specifically geared towards data mining. So you don't want to do your regular, little t-tests and stuff on these, but there's RapidMiner, and there's Nime and Orange. And those are all really nice to use because they are control languages where you drag nodes onto a screen and you connect them with lines and you can see how things run through. All three of them are free or have free versions, and all three of them work in pretty similar manners. There's also BigML, which is for machine learning. And this is unusual because it's browser based. It runs on their servers. There's a free version, although you can't download a whole lot. Doesn't cost a lot to use BigML, and actually is a very friendly, very accessible program. Then in terms of programs you can actually install for free on your own computer, there's one called SOFA Statistics. That means Statistics Open for All. Kind of a cheesy title, but it's a good program. And then one with a web page straight out of 1990 is PAST3. This is paleontological software. On the other hand, does do very general stuff. It runs on many platforms, and it's a really powerful thing, and it's free, but it is relatively unknown. And then, speaking of relatively unknown, one that's near and dear to my heart is a web application called StatCrunch. It costs, but it costs like $6 or $12 a year. It's really cheap, and it's very good, especially for basic statistics and for learning. I used it in some of the classes that I was teaching. And then if you're deeply wedded to Excel and you just can't stand to leave that environment, you can purchase add-ins like Excel Stat, which give you a lot of statistical functions within the Excel environment itself. That's a lot of choices. And the most important thing here is don't get overwhelmed. There's a lot of choices, but you don't even have to try all of them. Really, the important question is what works best for you and the projects that you're working on. There's a few things you might want to consider in that regard. First off is functionality. Does it actually do what you want, or does it even run on your machine? You don't need everything that a program can do. I mean, think about all the stuff that Excel can do. People probably use 5% of what is available. Then there's also ease of use. Some of these programs are a lot easier to use than the others. And I personally find that the ones that are easy to use, I like them. And so you might say, no, I need to program because I need to do custom stuff, but I'm willing to bet that 95% of what people do does not require anything custom. Also, the existence of a community. Constantly when you're working, you come across problems, don't know how to solve it, and being able to simply get online and do a search for an answer and have enough of a community that there are people there who have put answers up and discuss these things. Those are wonderful. Some of these programs have very substantial communities. Some of them it's practically non-existent, and you get to decide how important that is to you. And then finally, of course, there's the issue of cost. Many of these programs I mentioned are free. Some of them are very cheap. Some of them run on sort of a freemium model, and some of them are outrageously expensive. So you don't buy them unless somebody else is paying for it. So these are some of the things that you want to keep in mind when you're trying to look at various programs. Also, let's mention this. Don't forget the 80-20 rule. You're going to be able to do most of the stuff that you need to do with only a small number of tools. 1 or 2, maybe 3 will probably be all that you ever need. So you don't need to explore the range of every possible tool. Find something that does what you need, find something you're comfortable with, and really try to extract as much value as you can out of that. So, in sum, in our discussion of available applications for coding and data science, first remember, applications are tools. They don't drive you, you use them. And that your goals are what drive the choice of your applications and the way that you do it. And the single most important thing is to remember what works for you may work well for somebody else. If you're not comfortable with it, if it's not the questions you address, then it's more important to think about what works for you and the projects that you're working on as you make your own choices for tools for working in data science. When you're coding in data science, one of the most important things you can do is be able to work with web data. And if you work with web data, you're going to be working with HTML. Now, in case you're not familiar with it, HTML is what makes the World Wide Web go round. What it stands for is Hypertext Markup Language. And if you've never dealt with web pages before, here's a little secret. Web pages are just text. It's just a text document, but it uses tags to define the structure of the document, and a web browser knows what those tags are and it displays them in the right way. So, for instance, some of the tags, they look like this. They're in angle brackets, and you have angle bracket and then a beginning tag, so body. Then you have the body, the main part of your text, and then you have in angle brackets and a backslash body to let the computer know that you're done with that part. You also have P and backslash P for paragraphs. H1 is for header 1, and you put it in between that text. TD is for table data, or the cell in a table, and you mark it off that way. If you want to see what it looks like, just go to this document, DSO331html.txt. I'm going to go to that one right now. Now, depending on what text editor you open this up, it may actually give you the web preview. I've opened it up in TextMate, and so it actually is showing the text the way I typed it. I typed this manually, I just typed it all in there, and I have HTML to say what a document is. I have an empty header, but that sort of needs to be there. This I say what the body is, and then I have some text. LI is for list items. I have headers. This is for a link to a web page. Then I have a small table. And if you want to see what this looks like when it's actually displayed as a web page, we'll just go up here to Window and Show Web Preview. This is the same document, but now it's in a browser. And that's how you make a web page. Now, I know this is very fundamental stuff, but the reason this is important is because if you're going to be extracting data from the web, you have to understand how that information is encoded in the web and is going to be in HTML most of the time for a regular web page. Now, I will mention something that there's another thing called CSS, and web pages use CSS to define the appearance of a document. HTML is theoretically there to give the content, and CSS gives the appearance, and that stands for Cascading Style Sheets. I'm not going to worry about that right now because we're really interested in the content. And now you have the key to being able to read web pages and pull data from web pages for your data science projects. So, in sum, first, the web runs on HTML. That's what makes the web pages that are there. HTML defines the page structure and the content that's in the page. And you need to learn how to navigate the tags and the structure in order to get data from the web pages for your data science projects. The next step in coding in data science when you're working with web data is to understand a little bit about XML. I like to think of this as the part of web data that follows the imperative, data define thyself. XML stands for Extensible Markup Language. And what it is, XML is semi-structured data. What that means is that tags define data so a computer knows what a particular piece of information is. But unlike HTML, the tags are free to be defined any way you want. And so you have this enormous flexibility in there, but you're still able to specify it so the computer can read it. Now, there's a couple of places where you're going to see XML files. Number one is in web data. HTML defines the structure of a web page, but if they're feeding data into it, then that will often come in the form of an XML file. Interestingly, Microsoft Office files, if you have docx or xlsx, X part at the end stands for a version of XML that's used to create these documents. If you use iTunes, the library information that has all of your artists and your genres and your ratings and stuff, that's all stored in an XML file. And then finally, data files that often go with particular programs can be saved as XML as a way of representing the structure of the data to the program. And for XML, tags use opening and closing angle brackets just like HTML did. Again, the major difference is that you're free to define the tags however you want. So for instance, thinking about iTunes, you can define a tag that's genre, and you have the angle brackets and genre to begin that information, and then you have the angle brackets with the backslash to let it know you're done with that piece of information. Or you can do it for composer, or you can do it for rating, or you can do it for comments. And you can create any tags you want, and you put the information in between those two things. Now, let's take an example of how this works. I'm going to show you a quick data set that comes from the web. It's at airgast.com and API. This is a website that stores information about automobile Formula One racing. Let's go to this webpage and take a quick look at what it's like. So here we are at airgast.com, and it's the API for Formula One. And what I'm bringing up is the results of the 1957 season in Formula One racing. And here you can see who the competitors were in each race and how they finished and so on. So this is a data set that's being displayed in a web page. If you want to see what it looks like in XML, all you have to do is type XML onto the end of this .xml. I've done that already, so I'm just going to go to that one. You see, it's only this little bit that I've added .xml. Now, it looks exactly the same because the web page is structuring XML data by default. But if you want to see what it looks like in its raw format, just do an option click on the web page and go to View Page Source. At least that's how it works in Chrome. And this is the structured XML page. And you can see we've got tags here. It says race name, circuit name, location. And obviously these are not standard HTML tags. They're defined for the purposes of this particular data set. But we begin with one, we have circuit name right there, and then we close it using the backslash right there. And so this is structured data. The computer knows how to read it, which is exactly, this is how it displays it by default. And so it's a really good way of displaying data, and it's a good way to know how to pull data from the web. You can actually use what's called an API, an application programming interface, to access this XML data, and it pulls it in along with its structure, which makes working with it really easy. What's even more interesting is how easy it is to take XML data and convert it between different formats because it's structured and the computer knows what you're dealing with. So for example one, it's really easy to convert XML to CSV or comma separated value files. That's the spreadsheet format, because it knows exactly what the headings are and what piece of information goes in each column. Example 2, it's really easy to convert HTML documents to XML because you can think of HTML with its restricted set of tags as sort of a subset of the much freer XML. And 3, you can convert CSV or your spreadsheet comma separated value to XML and vice versa. You can bounce them all back and forth because the structure is made clear to the programs that you're working with. So, in sum, here's what we can say. Number 1, XML is semi-structured data. What that means is it has tags to tell the computer what the piece of information is, but you can make the tags whatever you want them to be. And XML is very common for web data, and it's really easy to translate the formats XML, HTML, CSV, so on and so forth. It's really easy to translate them back and forth, which gives you a lot of flexibility in manipulating data so you can get into the format you need for your own analysis. The last thing I want to mention about coding and data science and web data is something called JSON. And I like to think of it as a version of smaller is better. Now, what JSON stands for is JavaScript Object Notation, although JavaScript is supposed to be one word. And what it is that like XML, JSON is semi-structured data. That is, you have tags that define the data so the computer knows what each piece of information is. But like XML, the tags can vary freely. And so there's a lot in common between XML and JSON. So XML is a markup language. That's what the ML stands for. And that gives meaning to the text. It lets the computer know what each piece of information is. Also, XML allows you to make comments in the document, and it allows you to put metadata in the tags. You can actually put some information there in the angle brackets to provide additional context. JSON, on the other hand, is specifically designed for data interchange. And so it's got that special focus. And the structured JSON corresponds with data structures. It directly represents objects and arrays and numbers and strings and booleans. And that works really well with the programs that you use to analyze data. Also, JSON is typically shorter than XML because it does not require the closing tags. Now, there are ways to do that with XML, but that's not typically how it's done. As a result of these differences, JSON is basically taking XML's place in web data. XML still exists, still used for a lot of things, but JSON is slowly replacing it. And we'll take a look at the comparison between the three by going back to the example we used in XML. This is data about Formula One car races in 1957 from airgas.com. And so you can just go to the first web page here, and then we'll navigate to the others from that. So this is the general page. This is if you just type in without the .xml or .json or anything. So it's a table of information about races in 1957. And we saw earlier that if you add just .xml to the end of this, it looks exactly the same. That's because this browser is displaying XML properly by default. But if you were to right click on it and go to view page source, you would get this instead. And you can see the structure. This is still XML. And so everything has an opening tag and a closing tag and some extra information in there. But if you type in .json, what you really get is this jumbled mess. Now, that's unfortunate because there is a lot of structure to this. So what I'm going to do is I'm actually going to copy all of this data. And then I'm going to go to a little web page. There's a lot of things you can do here. And it's a cute phrase. It's called JSON Pretty Print. And that is make it look structured so it's easier to read. I just paste that in there and hit Pretty Print JSON. And now you can see the hierarchical structure of the data. The interesting thing is that the JSON tags only have tags at the beginning. So it says series in quotes and then a colon. And then it gives the piece of information in quotes and a comma, and it moves on to the next one. And this is a lot more similar to the way that data would be represented in something like R or Python. And so it's also more compact. Again, there's things you can do with XML, but this is one of the reasons that JSON is generally becoming preferred as a data carrier for websites. And as you might have guessed, it's really easy to convert between the formats. It's easy to convert between XML, JSON, CSV, etc. And so you can get a web page where you just paste one version in and you get the other version out. There are some differences, but for the vast majority of situations, they're just kind of interchangeable. So, in sum, what do we get from this? Like XML, JSON is semi-structured data, where there are tags that say what the information is, but you can define the tags however you want. And JSON is specifically designed for data interchange. And because it reflects the structure of the data in the programs, that makes it really easy. And then also because it's relatively compact, JSON is replacing gradually XML on the web as a container for data on web pages. If we're going to talk about coding in data science and the languages that are used, then first and foremost is R. The reason for that is, according to many standards, R is the language of data and data science. For example, take a look at this chart. This is a ranking based on a survey of data mining experts of the software that they use in doing their work. And R is right there at the top. R is first. And in fact, that's important because there's Python, which is usually taken hand in hand with R for data science. But R sees 50% more use than Python does, at least in this particular list.